All right, so my name is Walter King. I'm a member of the Huntsville Grotto and also an employee at NASA Marshall Space Flight Center. I'd like to thank Ray for inviting me to come talk to you guys, and I'm really excited to share what we do. So I'm going to tell you a little bit about one of the teams that I work on at NASA that's developing LiDAR mapping systems for mapping navigation on the lunar surface, but we are testing those systems in cave environments. So Ray, if you'll advance, please. And go ahead and play the video, it would be awesome. So this is just a bit of a teaser of the sort of thing you can do with this technology. So what you're seeing here is a quarry in Huntsville, Alabama called Three Caves. And this is a scan that we did with the instrument that we've been developing. So the colors that you're seeing are actually intensity. So that's sort of the reflectivity mapped to a color at every point in space. And it took us about 6.5 minutes to gather the data that we used to turn into this scan. And the path that you're flying through the video is the path that we actually walked when we gathered the data. So that path was about 370 meters walking along this walking path that runs through the quarry. So we're capturing a resolution down to about a centimeter, so you can see the rocks on either side of the path. In other caves, you can pick up formations, cracks, crevices, bacon, really you name it. And as we come out of the cave, you'll see there's some people standing around in the parking lot, some cars. And as the video sort of rises up from above, you also might notice that there's passages off at the outskirts of where we scanned that are kind of sparse, but we still caught points in them. So we didn't ever actually walk into those passages. Those areas were just sort of caught by the sensor as we walked through. So that's kind of a neat thing to see, that we're capturing data in places we didn't actually walk. And if you'll advance, Ray. So I'll give just a brief overview of our team and how this instrument works. So the instrument is called the Kinematic Navigation and Cartography Knapsack, or KNAC. And it's a LiDAR backpack that can map its surroundings as you walk through an environment wearing it. So the project's primary objective here is creating mapping navigation techniques that we can use on the lunar South Pole. And the PI, the principal investigator for the instrument, is Dr. Mike Zanetti, also out of NASA Marshall Space Flight Center. And the way this instrument works is we have a commercial off-the-shelf LiDAR unit, the sort of thing you'd find on an autonomous car. And then we also have an IMU, an inertial measurement unit, like you'd find in your phone, just much, much more accurate. And we take the data from that IMU and from the LiDAR unit and feed it into something called a simultaneous localization and mapping algorithm. It's essentially a computer program that matches up those snapshots from the LiDAR instrument and tries to stitch them together into one big expansive map, like you can see at the bottom of that slide. And so this technology is great because it doesn't care about illumination conditions. It's an active source sensor, so it can see into the dark whether there's visible light or not. It doesn't need GPS. It can map very quickly, and it maps in a lot of detail. So that's great for both space exploration and cave exploration. And as an added plus for space exploration, this is the kind of thing that could be relatively easy to integrate with a spacesuit or a moon buggy or a lunar rover, that sort of thing. And I'm sure that, we've all done analog cave survey or even cave survey with digital instruments. Doing that in a spacesuit would be pretty hard. So this is another option here. Is everybody hearing me okay?
Yes.
Okay, awesome. I just saw one person was having audio issues. And so if you'll click to the next slide, Ray, that'd be awesome. So I want to give just a little bit of context for why our team is interested in testing in terrestrial caves and why the space community in general is interested in caves. So we believe that there are caves throughout the solar system, actually. So on the moon, on Mars, on other planetary bodies. And we know this from orbital imagery. So we've identified what some people call subterranean access points in plain terms, what we think are cave entrances. And on the right, you can see some examples from the moon and from Mars. And the space community cares about these because, one, they probably hold a wealth of scientific information. For instance, caves on the moon could be billions of years old. The crust doesn't recycle in the same way it does on Earth, so they could hold lots of information about the history of the moon and by extension the Earth and the solar system at large. And they're also of interest to the space community because they could be places for habitation, essentially to put a lunar base, because you're shielded from radiation and the thermal environment is much more constant. And then lastly, some researchers think that there could be resources down in these caves. So things like water ice, solid methane, that sort of thing, things that could be used to sustain, a permanent human presence on these bodies. Right, if you'll move to the next slide. Why our team specifically is interested in caves here on Earth is because they're the best analog that we have for caves on the moon or on Mars. And if we want to go and visit those places and map them with this kind of technology, we need. And another reason that we want to test in caves here on Earth is they're not only great analogs for caves on the moon or on Mars, but they're also good analogs for the surface of the moon, Mars, and other planetary bodies, which is an objective that's more in the forefront of space exploration. So terrestrial caves are great analogs for both caves in space and planetary surfaces because you don't get GPS underground. They're really rugged and irregular and hard to navigate. And there's no light. And on some places like the lunar surface, you get lots of big, long shadows and permanently shaded areas that are hard to actually see within and know what's there. And lastly, we all know that if something's too heavy or too bulky, you're going to have a hard time actually taking it very far into a cave. And that constraint also sort of applies to space exploration. It's not a perfect analogy, but if we're developing something that we can take deep into a cave system, we're bringing that technology closer to something that's going to be small enough and light enough to actually fly to the moon or somewhere else in the solar system. And another big advantage of testing in terrestrial caves is a lot of them, or maybe not the majority, but some of them have been mapped by other means using traditional methods. And that gives us a baseline that we can compare our system performance to. And I'll talk a bit about that more later. Ray, if you'll advance again. So some of the things you can do with this sort of technology in the context of planetary exploration and planetary caves, having this three-dimensional data can help in assessing the significance of a skylight feature or cave entrance as a place to go and do science or go look for resources or as a place to try to put a permanent settlement for habitation. And in addition to that, having a data set about the entrance of a cave on the moon allows you to sort of explore how you're going to actually design a mission that might go there, enter it, and explore it, whether that's robotic or a manned mission sometime, way in the future. And then lastly, of course, you're getting all this topographic data that can tell you things about geology, morphology, and the history of these different features. And a lot of that also applies to caves here on Earth. So having this three-dimensional data set, essentially a 3D model of the cave environment, can enhance studies of geology or morphology, how caves are formed, how water and air circulate underground, and also potentially even things like habitat inventory. So there's a lot of different applications. Next slide, please. All right, so I'll tell you a little bit about the field work that we've done. We've scanned 2 different caves. One I already talked to you a little bit about, the quarry here in Huntsville. And we also did a scan of Lava River Cave that's out in Arizona. So it's just north of Flagstaff. It's a lava tube that's about 700,000 years old. It's on public lands and it sees a lot of public traffic. So Ray, if you'll advance, I'll show you a fly through of that data. And if you can click to play the video, that would be perfect. So this map has almost 45 million points in it. And it took us just about 45 minutes to gather the data to create it. So essentially the time it took me to walk from the entrance to the back of the cave, that's the amount of time it took to generate this map. So the colors that you're seeing are, again, intensity values. So it's how reflective the different points in the cave were mapped to a color. And as we move through, you'll be able to see different features, rocks, boulders, that sort of thing. Now, I guess by caver standards, this this is a very easy cave to navigate. It's mostly walking passage. There's a little bit of stooping, one place where you had to crawl with instrument, but largely pretty easy to navigate. And as we move through and come around a corner, eventually we're going to come to a bifurcation, a split in the passage. And we only process data from walking down that right side of the passage. And I think it's coming up here. But something that you'll notice as we come through that right-hand fork, you can see the video sort of dip down. That was probably the lowest ceiling in the cave, probably 3.5 feet maybe. That was the only place that we really had to crawl with instrument. And as we come through here, if I remember right, this is probably the tallest ceiling in the cave, maybe 30, 35 feet. Ray would know better than I would. But if you look at the ground, you also see that there's a fracture that's running all the way down the middle of the passage that the LiDAR picked up very well. And also some people there on the right. So there were a lot of people in the cave the day that we scanned. Ray was a huge help and was trying to get people to stand still as we pass by, because having objects or people moving the scene can actually degrade the quality of the scan and cause it to sort of drift one direction or another. So you might see some people throughout the scan. You also might be able to see some cracks on the floor. We were able to pick up cracks, boulders, also some lava ripples, and some piles of splashdown and another breakdown. And so we should be coming right towards the end of the cave now. And as we rise up above, it's kind of an interesting...
There's a ghost in the back.
To view the cave from. Sorry, Ray, what was that?
There was a ghost in the back of the cave.
Oh, yeah, I noticed that. Yeah, but it's an interesting perspective. And also, if you take a look at that split in the cave, you'll see that one side is really sparse, but we never actually processed any data from when we walked through that fork of the cave. So all the data that you see there was captured just by walking up to that split, taking the other passage, and then continuing on down the cave. So even though we never set foot in that passage, we caught enough points just by walking past it to somewhat characterize it, which is pretty cool. And if you'll advance to the next slide, Ray, there's a lot of different things you can do with a data set like this. So this is just one example. This is that point cloud co-referenced with a digital elevation model that's publicly available. And you can see some interesting things. If you look at it from the side, you'll see that the cave actually stays at a pretty constant elevation above sea level, but the topography actually rises above it. So you're deeper at the back of the cave, even though you're kind of at the same elevation as sea level, which is neat to be able to see things very intuitively that way when you're combining data sets like this. And if you'll advance, Ray. One thing that we were really interested in was essentially how well did we do? How good is this scan that we did? How accurate is it? So that's something that we looked into. And luckily, Ray was kind enough to share this map that he had drafted, and not only share the map, but also share the original survey data that was used to generate the map. So that was hugely helpful in sort of comparing how accurate this LiDAR scan is. And Ray, if you'll advance, when we lay the LiDAR over the cave map, just sort of roughly, you can see it's pretty similar, but it's not exactly the same. It's a little bit different. So we dug into that a little bit more. And Ray, if you'll advance to the next slide, I'll talk a little bit more about that. So I took that survey data, I threw it into Compass, generated this line plot, and then exported it in a format that we could bring into the program that we used to work with point clouds. Then I tried to line them up as best that I could. So I lined them up based on the entrance, because we're pretty confident in the accuracy of the scan at the entrance. And I lined them up sort of based on what probable station locations would have been and what some plausible shots, from the entrance into the cave would be. And you can see that they diverge quite a bit. And we're actually quite confident that the survey that Ray and others did in the 1980s is very accurate, thanks to some work that Paul Jorgensen did. He did a radiolocation point at the back of the cave, And if you plot that radiolocation point on top of the line plot, it is smack on top of the line plot at the end of the cave. So we're pretty confident that that survey in the 1980s is very accurate, and it's actually our LiDAR scan that has drifted off of the true path of the cave. So by the time we get to the back of the cave, we're seeing a discrepancy of about 144 meters, which is significant. But you can also think of that as sort of an accumulated azimuth error as you're moving through the cave, because errors build up near the beginning and those propagate all the way back as you do the scan. And right, if you'll advance again, that's just another way to think about the error that we're seeing here. A couple interesting things. First, in the vertical direction, the LiDAR scan was extremely accurate. We never saw a deviation more than about a half meter from the 1980 survey, which is interesting. And the other thing is, I found that if I divide up the point cloud in 3 places, and then just ever so slightly sort of translate and rotate those sections, the point cloud will line up very well with the line plot. All of the survey stations and all of the shots will be within the bounds of the point cloud. And so what that sort of suggests is that there are portions of the point cloud that are highly consistent with the original survey of the cave. And Ray, if you'll advance and maybe just click again to go ahead and put that animation up there. So what we think might be happening is that the error is not being introduced evenly throughout the scan. So we think that there might be areas of very low error and then areas of very high error that make up this total, accumulated error. So pointed out on that map are some places where the terrain was really rough and we were jostling the instrument around a lot, or we were stooping or crawling. You can see that some of those places that we divided the map to make it line up best with the line plot are close to those low ceilings or places we think we were jostling the instrument a lot. So, and another thing to consider, like I mentioned, is there are lots of people moving in the cave. That could have introduced areas of, I guess, increased error that sort of drive up the average error in the scan. But so we're looking at ways to improve the global accuracy because we do see a good bit of drift from what we know to be true. We think that maybe processing more of the data would help. So we took data the whole way in and the whole way out, but we only processed the data on the way in. So perhaps if we process all of it, we'll get better results. We're also curious if there are different parameters in the algorithm that we're using that we could tune to be better suited to mapping in cave environments. Then lastly, at some point, we're interested in seeing if we can take other data sets, things like radiolocation points or survey stations, known locations from other ways of mapping the cave, and constrain how the algorithm converges on a solution with those to get a better global accuracy. And Ray, if you'll advance again. So even though we see some drift at the global scale, where this technology really shines is when you're sort of looking at the local scale, the fine scale features. So Ray, if you'll advance, looking at an excerpt from the 1980s map, you can see that there, some extensional fractures, some boulders, some lava ripples. All of those features are very well represented in the LiDAR and are pretty easy to see. The lava ripples are a little harder to see, but if you tweak the way the color mapping works, those become very distinct. So you have a lot of flexibility in how you actually display the data. And if you'll advance again, Ray, and you can just click through to do the animations. Again, you can see that these boulders are visible in both, but something that's picked up on the LiDAR scan that isn't included in the paper map is this long fracture that runs down the middle of the cave. And we all know that what actually makes it into a sketch is kind of subjective, and it's kind of at the discretion of the sketcher. And if we drew every little detail of a cave passage into our sketches or into the maps, things would probably pretty quickly become unintelligible. There'd just be too much information. Things would be too cluttered to really make good sense of it. But that's one of the huge advantages of LiDAR, is it does capture every single detail down to the centimeter scale. And it's able to display that in a way that is intuitive and understandable and comprehensible. And if you'll advance again, Ray, something else that's really valuable about having a 3D data set like this is you can take cross sections anywhere you want after you've left the cave after the fact. So this is just an example. We took a cross section and a place to create something similar to what was done in the survey in the 1980s. But we could do this anywhere in the cave, in a matter of, maybe a minute. And if you'll advance one more time, the last thing I want to hit on is that having this 3D data set really captures the nature of a cave more holistically than you can in 2 dimensions. So in the paper map, and also when looking at the LiDAR from above, we see these 2 boulder piles that look really prominent. Well, if you're looking at them from the side, maybe you're walking down the passage, they're not quite as obvious. So if you're trying to use that as a navigational aid or something of that sort, something to consider. It might not be as obvious as it looks in the map. So having a 3D data set that you can look at from any angle is really a more holistic and useful representation of cave environments. And if you'll advance again, Ray, I'll try and wrap up. So there's a little bit of time for questions. I know we got a little bit of a rough start. So we're still working on this. We're planning to continue doing testing in cave environments. Right now, something I'm working on is taking the components of the system and repackaging them in a smaller form factor in a way that's going to be more amenable to caves and other harsh environments. So we're thinking we might be able to fit everything into a 6 liter and a 3.5 liter Darren drum. And then all that could go in a 15 liter PVC cave pack that we know and love. And so that would really open up the possibilities as far as where we can access and go and scan with the system, because there are lots of places that we just can't get the system as it previously was due to the size and weight of it. And the other thing that's sort of right on the horizon is we're planning to do some scans of vertical caves. So we have the equipment to do a high line and a haul system and all that. And we're hoping soon, once we get some logistics and approvals and all that worked out, that we can go out and lower this instrument down into some pits and see what sort of data set we get from that. And so that's a good analog for hopefully one day in the future sending an instrument like this down a skylight on the moon or on Mars. And yeah, so that's the motivation for that work. And then lastly, at some point, we would like to try and augment the scan with other types of data, so radiolocation points or traditional surveys, so that we can improve that global accuracy. So to conclude, the NAC team is doing testing in cave environments, and we're doing that as a way to develop technologies for mapping navigation on the lunar surface. But as a side effect of that, we're also producing things that could be really valuable to cave exploration and study here on Earth too. So this technology is great for space exploration or cave exploration because it is agnostic to illumination conditions. It can see in the dark. It's an active source sensor. It doesn't need GPS. It produces surveys very quickly and with a lot of detail. And we're able to capture just about every detail in the cave environment down to about a centimeter. Now, there is some drift at the global scale. So we know that at the global scale, these results aren't perfect, but that's something that we're working on. And the last thing, there's one more thing I want to leave you all with. So both Alabama and Arizona, well, if you could go back, Ray, sorry about that. Both Alabama and Arizona have thriving space communities, and both Alabama and Arizona have a wealth of cave environments. In Alabama's case, it's karst. With Arizona, it's karst and volcanic features. And these spaces are in a lot of ways analogous to some environments in space, on the moon, Mars, other places. And so if they're used responsibly, they can really be a way to advance technology development for space science, and also advance speleology at the same time. So that's a collaboration and something that I'm interested in fostering. So I'm hoping to see more of that moving forward. All right, and if you flick to the last slide, a lot of people to thank, of course. The people that funded the research, and also a special thanks to Ray for inviting me to speak, and also Ray and Paul, and also the Central Arizona Grotto for sharing data, and also helping out the day we scanned the Lava River Cave. And maybe back it up to the conclusion slide so we can see that. And if anybody has questions or has suggestions on places that would be good places to go and scan, let me know. Yeah, let me know if you've got any questions.
Walter, can you hear me?
Yes, I can.
This is Steve Smith, the chair. Your work here reminds me, I was at the NSS convention, must have been 13, 15 years ago, and they had a panel of distinguished people, and the topic of the panel was the future of caving. And
Right.
they were saying that they could foresee, maybe even our lifetimes, that your helmet will become a sensor array. It'll be taking temperature, humidity, LiDAR, mapping, and your work here, getting ever smaller, ever more compact. We could be well on the way to that ultimately your helmet is a complete sensor array.
Yeah, I don't disagree with that statement. There's still a ways to go. One of the big challenges right now is we need that inertial measurement unit to allow the algorithm to piece things together. And that's bigger than the sensor. So the LiDAR sensors are actually quite small now. And honestly could go on a helmet right now, but it's the IMU that's sort of holding things up and makes things a little bulkier. But I think we're well on our way to that.
Hey there. Can you guys hear me okay?
I can.
My name is Blaze, and I would like to say thank you for giving such a great presentation showing the potential limitations of LiDAR, especially mobile LiDAR, when it comes down to doing cave survey. I had some questions for you that are kind of nerdy, so I apologize to other people on this. Okay, great. So the questions are, have you tried different SLAM algorithms such as LeoSAM or Wildcat or other sorts of available algorithms on GitHub for your data, and has that improved anything?
Sure. So I can only speak to this a little bit. So I'm not the person to talk to about the algorithms. That would be Kyle Miller, and I can shoot you his email if you want to talk shop with him about that. What I do know is that our algorithm is based on things that are open source projects on GitHub, and we pulled those down and made modifications and switched out different libraries and that sort of thing. Okay. And I can't tell you much more than that, other than that it's based on publicly available algorithms, but has been tweaked by our software engineers. But I'm sure Kyle would be perfectly happy to talk shop, and I can shoot you his email address.
That would be great, actually. If you can put that maybe somewhere in the chat or send it to Ray. The second question.
Yes, okay.
I'm assuming it looked like you were using Velodyne pucks with the IMU on the backpack mounted solution. So was it a single 45-minute loop for the entire cave, or did you try breaking it up?
Okay, so as far as actually, so the LiDAR sensors are actually Ouster OS ones that we use.
Oh, excellent. Okay.
Yeah, so they're similar. And I think Ouster actually recently acquired Velodyne, so now they're the same. Yep. But as far as the question about the loops, do you mean sort of processing the data in?
Yeah, so
say running the first 5 minutes of data and then running 5 to 10 minutes and then 10 to 15 is separate.
Yeah.
Again, double check with Kyle, but I'm 90% sure that this was a single loop. So we ran all the data from the entrance to the back of the cave in one go. But that would be interesting to look at because, like I was saying, we think